We had a slight problem with Donna's mic, so the audio does sound a bit boxier than usual. That means with more room echo. Thanks for understanding. G'day, Dr. Carl, Shirtloads of Science, University of Sydney. Today I'm very lucky to have with me Professor Donna Strickland. Did I get the pronunciation correct?
You did.
And you have made it big time. You've had a trip to the Blue Room, which is special scientific talk for the Nobel Prize. Oh my God.
I've never heard it described that way, but okay.
That's the euphemism. So you've got a Nobel Prize.
I do.
Wow. Man, that's very top level. You don't go any topper than that.
Not in physics, no.
Now, I've been trying to read up on it, and because it's with a Nobel Prize, it's not immediately obvious. Exactly, when reading the explanation of what you did, which is the chirped pulse amplification, I don't quite get it. And if I did get it, it wouldn't be worth a Nobel Prize, okay? So Can we start off, so you were born at a very early age, you grew up, and then what did you study?
Born at 0.
Born at 0, and then you kept on growing at 1 second per second, and you went to school, and how did you find school? Do you have any likes or dislikes in your subjects back then?
I think I liked all school in elementary school, and then I got less and less liking everything on the art side. And certainly I have no memory, so I hated to have to memorize a poem. But even worse than memorizing a poem was having to write a poem.
Oh, because understanding is better than having to memorize, isn't it?
I guess, and I have no memory. So it was really, really hard for me to memorize something, but it was even harder to write. I hate writing. I shouldn't say that, but I do.
Okay, so we're thinking you're heading down a pathway of being an experimentalist. Good with your hands.
I think I was probably thinking I would be a mathematician. I like puzzles, and I always thought of math as a puzzle, and my favorite subject, by high school, my favorite subject was math.
Just as a detour, what's your favourite equation or identity?
Oh no, just F equals ma.
That's a good one. That is really deep. When I was in New Guinea, I was teaching to students who'd never been in a car or an aeroplane or an escalator, had never experienced external acceleration. I took them through F equals ma on how the Americans got the rocket to the moon and back again. I was surprised at how deep F equals ma is.
That's right.
It's deep.
It seems like such a simple thing, and this is all we teach to first-year physics students, and still it's so hard and complicated when you get into it.
So at university you studied maths and...
No, I studied engineering physics at university.
Engineering physics, so there's
because I
maths
couldn't
and
decide if I wanted to... I decided not to go into math. And then I chose physics or engineering, and so then I chose engineering physics because I could walk the line without making a decision.
Right, that makes sense. And then what happened after your first degree?
I knew I wanted to study lasers, so that's even why I went to McMaster, because even their undergrads got to study lasers.
So what year was that?
In the 1970s.
So lasers got invented in 1960 with that guy from Hughes
Laboratory. Right.
So that was early stuff.
Yeah, so you didn't see lasers, so they sounded so cool, and so...
They are cool.
They are cool.
Okay.
Really.
So then
I went to Rochester for my PhD because they have a school of optics.
Rochester? In New York?
In New York.
Hang on, that's where Kodak used to be, so there are lots of optics and stuff.
That's why optics, not only that, Bausch & Lomb glasses was there, and so they started a school of optics because they needed people working in their industries.
Right. And then you were thinking, want to get a more powerful laser, because if powerful is good, then more powerful is even better, I'm guessing.
Exactly.
And you began to run into a problem which was that okay, just for everybody else and me, can you explain how a laser works? Light amplification by the stimulated emission of radiation. Can you take us through it?
Yes, so it started with Einstein, as so much of physics.
In 1917?
1917.
What a person.
Really incredible scientist. And so the original quantum, I would say, is Planck, and Planck was the one who figured out why black body radiation has the spectrum it has, and it was Planck that really decided that the light must have a minimum energy unit, which is what we call the photon, and that a single photon's energy is given by its color or its frequency or how rapidly the crusts come in the wave.
The wavelength.
Right, so it's the inverse of the wavelength, gives you the energy. So Planck started there. That was 1900. In 1917, Einstein wrote a paper about, they say it's about how the light is in thermodynamic equilibrium with the molecules, but how is that? How is light being in equilibrium with the matter? And so this is where the idea came about, is that if the molecule would absorb light, if the quantized energy of the molecule absolutely matched a photon.
If the energy is matched,
Absolutely matched, then it would be a resonant process and it would absorb.
if they exactly matched,
the
you would have a resonant process.
That's right. But then he also showed, I think people sort of understood that, by just watching a shadow, that we absorb light and it doesn't keep going through without really understanding the quantum part. But what wasn't so well known is that if you were in the excited state, the process was the very same process. Stimulated emission is the very same process as absorption, but you start at the top and go down to the bottom in stimulated emission. And there's only one other process, and that's spontaneous emission. If you put something in the excited state, it only can stay excited. Like none of us can run forever. We can lie down in the bed forever, but we can't run forever.
Or you can pump an electron up to a higher energy level.
And
but
eventually it's going to want to fall down.
It's going to want to fall down.
That's called spontaneous emission. So those are the only three things you can absorb: stimulated emit and spontaneous emit. So there's two down and only one up.
So what are the three again? There's
Absorption up,
Yep.
stimulated emission down,
or
and spontaneous emission down.
One up, two down. Gotcha.
One up and two down.
Yep.
And so in this 1917 paper, he showed that the rate up is identical to the rate down.
He showed that.
Yes.
Didn't they know that?
No.
Wow.
They've never discussed stimulated emission either. He's the one who really brought this idea that the quantum levels would have to be the same and that the one down equaled the one up.
Wow.
And then he also showed that it's with the spontaneous emission, which that one he sort of did classically because there was nothing causing it, just eventually decays, that all of that equilibrium would happen and you would get this curve. And so it was from understanding these three processes that people eventually got to a maser in the 1950s and a laser in 1960s.
So the maser is M for microwave and laser is L for light.
That's right. And the lower the photon energy, the easier it is to make a laser.
The lower the photon energy, so the more you get into the radio and the infrared.
Well, they started with microwaves, but
Microwave.
we still haven't gotten an X-ray laser yet. And the reason is that to have the higher and higher energy, then the quantum level's higher and higher. Then the more energy you put in here, the faster it's going to want to fall down.
It's going to fall down by itself.
It's spontaneous emission just gets so fast that you have to pump so hard to beat the spontaneous emission. So that's why it's harder and harder as your energy goes up.
Okay, so now you're a PhD student, living on noodles or whatever they live on. And then how did you go down this pathway thinking, I've got to make a laser more powerful and this is how I'm going to do it? What happened?
Well, of course, that's probably a lot to do with my supervisor as well. But we had tried different things. But again, science isn't a one-person does thing. We're all just cogs in a wheel. And in 1984, we went to a conference, and at that time in 1984, all the rage in the ultrafast laser world was trying to take pulses that were on the order of 100 picoseconds, and a picosecond is a millionth of a second.
So that's 10 to the minus 12.
A picosecond is 10 to the minus 12, and so it was 10 to the minus 10 seconds long. And so that came from this laser that operates at 1 micron wavelength.
1 micron, so it's just in the infrared.
It's it's in the near infrared. Whereas optical communications is at 1.5 microns, so it's even longer than that.
Oh, really? Is that what they run at?
Yes, that's always run at 1.5 or 1.3, but mostly 1.5. And that's because that's where the losses are the lowest, so you can go kilometers without losing the light. So they already had fiber optic communications for that wavelength, but it just happened that Corning, a fiber optics company, had made this new fiber for 1 micron, and people were putting their 1 micron laser into it and turning up the power, and they saw that through nonlinear optics in the fiber, it was creating more bandwidth. And if you have more bandwidth, you can have a shorter pulse.
Hang on, more bandwidth. Now, I thought that a laser was just a single frequency.
Yeah.
You know, like pick a number, 700 nanometers. And you're saying that it spreads?
So if you want a short pulse, you must have a lot of colors, actually. If you have just one color, and so you have that one perfect wavelength, you only have one perfect wavelength if that one perfect wavelength goes forever.
So it's just a square wave. It's 575 nanometers or
It's
whatever.
not a square wave, no. Well, it would be, but the square would have to go for infinitely long.
Hang on, say that again?
So if you want just one single frequency,
Yep.
it has to go forever in time.
Right.
That's one single frequency. If you want a very, very short pulse, you have to have an infinite spectrum. They're inversely proportional to each other.
But how do you get a bunch of spectra out of a laser? Because normally a laser is just monochromatic.
Well, the reason it's monochromatic is that actually, again, the how wide the spectrum would be is given by that spontaneous emission time. So when it's up there, since it won't sit up on that level infinite amount of time, and it decays in time, that there is an uncertainty. This is, some people call it the Heisenberg uncertainty principle. I just call it Fourier transform theory. Fourier came before Heisenberg. And so, again, that time says there's an uncertainty. That exact one frequency would have to be there forever.
My primitive thinking was that there's just a single frequency, but it's not. It's actually covering like maybe 0.2 of a nanometer or 0.1. It's not like zero width. It's got a certain width.
It can't be zero width, and also it's not really that gives the real, if you really want a single line laser, a laser also has to have a cavity. And a cavity is like seeing with a string and making a standing wave in a string pattern. If the light goes around, it has to come and see itself again and not destroy itself by destructive interference. So you have to have given wavelengths. And the fundamental wavelength is a half a wavelength is the length of the cavity, because it would come around and meet itself again. Or you could have one wavelength that would meet itself, or three of them would meet itself. And so those are the only waves allowed. And so you have a sort of a picket fence of those wavelengths or frequencies allowed. And if you only want a single line, you make sure your bandwidth is this wide, and it's just the very narrow cavity mode. That's your single one.
Right.
But the short pulse laser people want an actually really long, wide spectrum, and probably has several of those quantum levels.
Peaks.
It has several quantum levels at play because it wants this huge bandwidth, and then there'll be maybe like 1,000 to 1,000,000 of these modes lasing all together.
Now, as I understand it, the problem was, as they went to higher powers, that the power would distort the medium through which the laser beam was travelling, limiting the power. Did I get that bit right?
Close.
Close.
It doesn't distort the material, it distorts the laser pulse itself.
It distorts the laser pulse itself.
Yeah, so a classical way to think about it is that the normal refractive index, which causes you to slow down, is the fact that the electric field is a wave, and it pushes the negative charges one way and the positive charges the other way. And then when the wave changes the side, it just sets up this oscillating dipole of charges, and that re-radiates. But just like you pushing a kid on a swing, when you push the most, that's not when they're moving the fastest, and so it's out of phase. And that's the slowing down of light. That's why light slows down in any medium other than vacuum. But now, again, if you can remember swinging on a swing, if you get really up high, you end up being there for a little bit and then come back down.
Right.
You no longer make that perfect sinusoidal up motion or cosine this motion. You actually sort of square wave yourself a bit. That's nonlinear motion. And so when you do that, you actually change the index of refraction, or the speed the light goes, with intensity. And so now you would have this beam of light going, just a big flat beam, but the very center of the beam is the most intense part. And so it travels slower, so this is why it curves around. And if it curves around, that's like going to a focus. But now it's curving, and a smaller beam, more intense, curves faster, 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 and this is called self-focusing. And this is what we had to work around. The beam actually, even though you would send in quite a big beam, it would focus down. And how fast this happens is how powerful the beam is. And now we have a short pulse in time. The very beginning of the pulse has no power. It goes through as a flat beam. But then as it gets more and more powerful, it damages there. And the peak of the pulse damages really quickly, and so it damages here and then back again. And so this is why we ended up in our beautiful, big, expensive glass laser rods, a very tiny line of damage. If you can imagine if it had been gelatin and you put a hypodermic needle and pulled it back out and left that track of damage, that's what it looked like.
There was
Yes,
physical
just a
damage?
Physical, oh yes, you would see a physical small little line right down the center of your rod, almost the whole length of your rod.
What sort of diameter?
It'd be
Like
less
a
than
pin?
100 micron. Yeah.
Like 100 microns. A hair is 50 microns.
50 micron, about the size of a hair. Yeah, it would just be a
You
hair.
could see that.
Yes.
And what sort of power were you dealing with? Like, obviously not watts. Were you kilowatts or megawatts or?
Well, it's gigawatts.
Okay, just to put this in perspective, if every electrical generator in Australia was switched on, we could generate 100 gigawatts, the whole of the country.
Right.
And you were getting gigawatts of power.
But only in a picosecond of time.
But only
the energy is very small.
Very small. Okay, so now you got this problem, everybody's got this problem, and suddenly you think, aha, I know what I'll do. I'll invent chirped pulse amplification. No, it didn't happen like that. No, so how did you do it?
So in 1984 we go to this
84.
conference. So they were putting this powerful ones in fibers, but fibers actually guide the beam. So now it doesn't matter about self-focus, and the beam has to be guided and stay straight.
Yep.
But you still have the problem that you have a pulse in time.
Mm-hmm.
And this front of the pulse travels the speed of light in glass,
Yep.
which is 1.5 times less than the speed of light in
Oh, that's a refractive
vacuum.
index of
That's
glass.
a refractive index. And the back of the pulse moves. Usually I have a slinky to explain this. But so if you can picture in your mind a slinky, and every loop in it is the phase front.
Ah.
Okay, now, so you pull that out. The front would be moving at the same speed as this guy. So in the stand, in its frame, it's here.
Yeah.
But the center one, imagine pulling it back, because it's moving slower. It's the most powerful one. So it's moving slower, so pull it out. You've pulled all those slinky coils apart here, but push them all together here. And the distance between the crests is the wavelength. So you make red colors at the front of your pulse and bluer colors at the back of your pulse. And this is how we made more bandwidth inside the fiber. And so we go to this conference. People are showing that you could make all these extra colors, and it was already known that you could use a pair of gratings that would make the colors go in the opposite direction and get a really short pulse.
Mm-hmm.
And one paper in particular showed if you want to do this really well, you have to actually use a long fiber and let it stretch out really, really long through dispersion. You keep making the colors.
Mm-hmm.
The problem with the cell phase modulation is that you would start with omega naught, because low power, nothing's happening. You would make red colors. At the peak, you would make back to omega naught. Then you would make blue colors and back to omega naught. We had no way to compress that because the colors.
So you're stretching, but you
So
can't compress.
now again, remember with the slinky idea, is that on top of that you have dispersion, which makes the red travel faster than the blue. So at the beginning of the pulse, you're making red more, and it's traveling faster. And you're making blue, and it's traveling slower. And then you're making more red traveling faster and more blue traveling slower. And so as it went through a longer and longer fiber doing this, you ended up with what's known as a linear chirp. The pulse
Chirp?
chirp.
Why the word?
Chirp.
Give me the name. Why did he?
So a bird's chirp
Yeah, go
is the
on.
fact that the audio frequency changes in time. So it's like, whoop,
Oh,
that's
okay.
a chirp.
Right.
Okay, so, and that's a red to blue chirp. So this is what we ended up having, is that if you use these really long fibers, you would have the red pulse, the pulse would go from red frequencies to blue frequencies. And if you had this nice linear chirp where it just linearly changed in time, we had a way of putting all those colors back together. And so it just happened that the one paper said, make the pulse really long, and then you can make it really short. And so that was the idea, because we knew, Gerard already knew that we had to figure out some way to make the pulse long so you could safely amplify it without getting to high peak powers.
Mm-hmm.
And then when it's out of the amplifier, compress it and make it short. But we didn't really know the fiber part. And when we saw that, it was like, there's the answer.
And what sort of length of optic fibre are you talking about? Like a centimetre, a
No, 3
kilometre?
kilometers.
Kilometres.
Should have had probably 4 kilometers, but I broke the fiber and I only had 1.5 kilometers.
Hang on, just say that again. You broke the fibre.
Broke the fiber.
Isn't that considered sad or naughty or suboptimal?
Suboptimal. But you can only get sad for so long. It's all I had, so that's what I
So you
used.
just went with it?
Yes. And
Really?
so then that's why I
So you-
damaged a few of my rods, so we couldn't turn up the energy all the way.
So you broke the rod and you
No, I
went
broke-
with
so
it.
the fiber, unfortunately, it was very nice. Corning donated the fiber. Gerard asked them to donate, and they donated 2.5 kilometers of the specialty fiber. But most people that want 2.5 kilometers of fiber want to lay it across 2.5 kilometers. And so they only had one end showing, and I had to get the light in and out.
And you couldn't find the other end?
Right, no, it was tucked underneath it, so I had to unspool it and re-spool it, and doing that, I nicked it
Oh, you
somehow.
poor thing.
Because I didn't even have another spool, I just had to put it on a film can with corks.
How
So
did
I
you
just
feel
did
at
this.
that moment when it broke? Did you go,
I don't remember.
God, thank God. But nevertheless, you kept on going
Have
with
to.
a shorter,
For a shorter fiber.
and what happened?
It was long enough. I mean, we stretched it to 350 pico, which is a third of what you really needed to stretch it. We needed to stretch it for 1 nanosecond to make sure it would not.
But you couldn't do that.
We didn't have. Yeah,
So you went for
we had
third
no
of
way to
a-
splice it. Now we would have fiber splices.
A
to
third of
splice
a
it.
billionth of a second.
Yeah,
And
it worked.
oh my God.
We amplified it, we recompressed it, and it worked. And that I do remember. That was a Thursday night. I do remember that.
And that So you must have had good hands.
Yes. In fact, I was the first one to use fibers, and back then we didn't have the fancy cleavers that we do now. Like my students get to use an electronic cleaver. I had to hold it in my fingers and take a diamond knife and just clip it like this, and the tension in my hands had to pull it apart. So after I did it, we had a few more students doing fiber pulse compression, and I was the one who could really hold the fiber and cleave it for them.
Oh, wow. My God, so it was a combination of...
This is why I call myself a laser jock.
You're a laser jock. So it was a combination of your inherent mechanical skills, plus your training,
Right.
plus your hard work
Right.
for years and decades, and maybe a little bit of luck. That
A lot of luck. You need a lot of luck.
Luck is good,
Yep.
and it worked out.
It worked out.
Oh, my God! Did you feel good when it actually was
Absolutely.
able? Oh my gosh! And so you went from gigawatts per square centimeter to...
We got to finally we had to add 2 more amplifiers after that one, but then we were able to do experiments at 10 to the 14 watts per square centimeter.
10 to the 14. That's 10 to the 14. You're in
Watts per square centimeter, not 10 to 14 watts. 100 terawatts per square centimeter, but that's because we focused it down tight. So we just had 100 millijoules in a picosecond.
That is a huge amount.
So 10 to the 11 watts.
Wow.
But we couldn't, we had actually the laser, we called it tabletop terawatt. The laser could do the full joule, so we would have had a terawatt laser system. But the thing that cost a lot of money are the gratings. And so we could only afford a grating that could have 100 millijoules on it. The gratings damaged way easier than the laser.
The gratings
rods.
damage.
The gratings are gold coated, and they have these lines that are 1800. The grating I had at 1800 lines per millimeter. And so those very fine lines of gold damaged pretty easily.
Okay, and then the phone call. I've heard about this thing called the phone call, and it's not as though they try to find out where you've been and ring you up when you're awake or something. So
No, that's all. They ring you at 11 o'clock in the morning Swedish time.
what? Not local where you happen to be time.
No, because at 12 o'clock their time, they will go to press conference whether they've reached you or not. It's the press conference because it's on the news all the time. It's always noon.
So what was it like? Was it sort of... lay it on me. What was it like?
It's 5 in the morning for us.
Okay, 5.
So it's scary to get a phone call
Were you-
at 5 in the
you were
morning.
happily
I was
unconscious,
asleep.
dreaming?
Yeah, I was happily unconscious.
Yep.
We do still have a home phone.
A landline
landline.
phone. How sweet.
I know, isn't it? And I think they called Gerard first, my supervisor, who was in France, and so it would be 11 in the morning also for him. And they got my phone. That's the phone number he had for us. And so they phoned, because I had a pretty quiet life, so they didn't have any phone for me. And they called and they said, please hang on the line. This is a very important call from Sweden. And so then I'm hanging on to my husband.
Hey, you were thinking Sweden? Phone call?
Well, October 2nd,
were you
5 in the morning.
Were you beginning
Absolutely.
to think?
I was hanging on going, I think I'm winning the Nobel
Oh,
Prize.
no, oh my God, how exciting.
I know. But unfortunately, they had hung up on me.
What?
Yes.
What do you mean they hung up on you? You thought you were a Nobel Prize winner.
They think I hung up on them, but I was just holding a landline, so no. So then, after 15 minutes, because I am a rule follower, and they told me to hang on, and then we started thinking that it was fake. I went downstairs and got on my...
So you put the phone...
We finally put the phone down.
Put the phone down, so then you opened the line again?
Yeah, and I had an email from the Royal Swedish Academy saying, we can't reach you, please call us. And so I called the Swedish number.
How much did that cost?
I don't even know. I don't think we looked that up. We don't care.
I'll ring you.
Yeah, so we rang them and found out, and that's when they told me.
So what are the exact words? Dear non-Nobel Prize winner, you are now... What do they say?
No, they said, it was, the president of the Royal Swedish Academy phoning to let me know that along with Ashkin, who won Art Ashkin won half the prize, and Gerard and I shared the other prize, half of the prize.
And they said, we are honoured to tell you that you have
That I
won...
can't remember the exact
details.
words, yeah.
Oh my God. Now what's this about you not being a professor? Tell me the story there.
Full professor?
Well, before you... it said in Wikipedia, which must be true, that you thought, yeah, Professor Schmesser. Tell me the story.
Well, I think it means different things at different universities. And so certainly when you come up for tenure from assistant professor to associate professor, you're fired if you don't make associate professor. So of course you're going to go for it. I mean, you have no choice.
Right.
But to go for full professor at Waterloo, I couldn't see the point.
You couldn't see, but you could put professor in front of your name.
I guess that would be the only thing.
Did you get more money?
No.
Did you get more carpet in the office?
Nothing.
Heater? Air conditioning?
Nope. So I couldn't see the point.
Would it increase your workload?
No. No, I could be chair of the department if I wanted. I'd already sat on the Senate. I couldn't see what it got for me, so I didn't bother.
So did they eventually sort of massage you into becoming a professor?
They gave it to me afterwards. I didn't have to do anything other than won a Nobel Prize on my CV.
CV, Nobel Prize, won.
I got it done easily, yes.
Oh, look, Professor Donna, look, thank you so much, and I hope that your story will be an inspiration for so many people to go on that pathway and, I guess, follow what they love where it takes them, and sometimes you're lucky.
Yes, absolutely. Hope they're lucky.
Thank you so much, Professor Donna. What's the official title? Nobel laureate?
Yes. Nobel
Laureate. I'm very honoured. Thank you very much for coming on. Thank you. Shirtloads of Science is washed, spun and aired by the University of Sydney.